Hello. So this talk is going to be complementary to what Veronica already presented. It's going to be an overview, and for those of you who were at the ACM meeting, it's going to be nearly exactly the same. Sorry about that. So I'm going to talk about the wind tunnel artificial meteors. The problems with natural meteors is that we'll observe them remotely, and most of the time, we do not know anything about the object before it enters the atmosphere, especially for the small ones, but also for the bigger ones. We have some idea of the size for example, the bigger ones, 2023 CX1, but that's about it. We don't know about the composition. We don't know about the density. We don't know about internal fractures and so on. So that still prevents us from interpreting the meteor data. So the advantage of having an artificial meteor in the wind tunnel is that you control everything, the flow speed, you know exactly what's in there because you put it yourself. So you know the mass, you know the size, you know the density, you know the composition, and now you have a meteor. So that's, okay, you can't see, sorry, here it is. So this is the wind tunnel facility. So it's about 1.5 meters in diameter. So if you stand here, your head should be around here. So you have a plasma generated here, and there's a meteorite sample coming into the plasma, and a battery of cameras looking at what happens when you smoke a meteorite, basically. So you have cameras in optical wavelength, near infrared, middle infrared, and near UV, spectrometers, thermography, and so on and so on. So we reproduce the conditions of a 3.5 centimeters meteorite at 80 kilometers of altitude at nearly 12 kilometers per second. And we did this for 31 meteorite samples over 3 campaigns. Last year, I showed the result for the luminous efficiency, and today it's more a broader overview of the results. All of the results are currently under referee, and there will be a special issue in Icarus. So this is the Stalin meteorite. So this is show you what happens when you smoke a meteorite. So here comes the samples, and now it's burning, and you can see that it looks like a high viscosity. Okay, you see some pieces coming off, and it's very different from this Murchison meteorite, where you can see lots of very small droplets going on. So yes, it's fast. So this is similar to what we would probably interpret as a continuous fragmentation. Also, I don't know if you can see it, but there are some very small blue particles going upstreams, something we did not expect at all. Okay, so if we draw a general picture of the behavior, we have two extremes, like high viscosity, and the other one is continuous fragmentation. Like there was also a 3D cameras able to reproduce the 3D view of the sample as it disintegrates in the plasma. By doing so, we could also compute the recession line, and we realize it is not linear. We somewhat expected it because the mass of the whole sample is shrinking faster and faster. We had a low resolution near UV spectra spectrometer for the very last campaign, and we were interested in detecting carbon, which unfortunately we did not detect, but we did detect iron, magnesium, and silicate, something that is hardly detectable in optical wavelength. We made sure here that the plasma signal did not interfere with the signal from the meteorite itself. We also had a camera and a spectrometer in the mid-infrared. One of the reasons is that there are only a few frames in the mid-infrared taken in the early 2000s during the Leonids. We wanted to compare, and what we saw was no emission line, only black body radiation. And so we were able to compute the temperature of the surface and to compare it with other experiments. We found that on average, the temperature is between 1800 and 2200 Kelvin, again, which was very different from previous mid-infrared measurements. But we compare here in-lab Meteor at 12 kilometers per second, and the frames that we had were taken during the Leonids, so that's the other extreme of the velocity spectrum. Also, we had a look at the rise of the signal in mid-infrared and also in optical. So in the visible, it's very sharp. In the mid-infrared, the increase is more gradual. So this is the mid-infrared view, and this is the optical, the visible view. The angle of view is different. You have 90 degrees difference. So this is basically this part here. But basically, we saw roughly the same. Okay, so in conclusion, we were able to smoke a real meteorite in the wind tunnel. That was very fun. And we learned a lot of things. Again, we did not detect carbon, unfortunately, but we detect silicates in near UV. And mid-infrared observations might help us for future stratospheric experiments. Thank you.